Welcome back to the next video, everybody. This video is all about local Tate duality. So the setup is P will be a prime and X will be a G sub P module of order N. So remember, G sub P is the local Galois group at P. It's G sub Q sub P. We're going to let X star be the dual of X. So that's the Z homomorphisms from X to the nth roots of unity mu sub N. Okay, and of course, G sub P acts on X star by the usual dual action because G sub P X on X, that's given to us. So there's the usual contra-gradient or dual action from basic representation theory, just given by G X star of X is G of X star of G inverse times X. Okay, and then also note from, basic linear algebra, X tensor X star is of course isomorphic to mu N, and mu sub N lives in QP bar cross. And this isomorphism is as G sub P modules. So this is just kind of an important thing to keep in the back of your head. Okay, so theorem one. So what does local Tate duality say? Under the setup above, with the notation above, hi of GPX is finite for all I bigger than or equal to 0, and it's trivial for all I bigger than or equal to 3. This is why we only really bothered defining H0, H1, and H2 in the early videos in this chapter on group cohomology. It's because all of the higher cohomology groups are just trivial. Okay. 2, for I equals 0, 1, or 2, the cut product gives me a non-degenerate pairing from HIGPX cross H2 minus IGPX star to H2 GP QP bar cross. And we know this latter guy here is isomorphic to Q mod Z from a previous video. Okay. And then finally, if P doesn't divide N, well, remember N is the order of X from the previous slide, then the unramified classes H1 of GP mod IP X to the IP, H1 of GP mod IP X star to the IP are the exact annihilators of each other under this pairing when I equals 1. So in other words, guys here kill things here when you plug them into this pairing here. The output's trivial and vice versa. Okay, so the proof of all this can be found in Milne's Arithmetic Duality Notes, Chapter 1. In fact, that's just a good book to read in general. It was in my prerequisite information math you need for Fermat's last theorem video, I believe. So I'll call that book MAD from here on out. How about R? So we looked locally at P here, the Galois group locally at P. What about the Galois group locally at infinity? Or in other words, what if I replace G sub P here by G sub R, where R is the real numbers? Well, the HI of GRX are finite for all I. If we use the Tate group H hat 0 in place of H0, then it turns out that the order of H hat 0 GRX is the same as the order of HI GRX for all I positive, so that's nice. And yes, there is a non-degenerate pairing from H1 GRX cross H1 GRX star to Q mod Z. And there's another pairing, H hat 0 of GRX cross H2 of GRX star to Q mod Z. And then there's a third pairing where you switch H hat 0 and H2 here. Okay, so things work sort of more or less like they did locally at P, but we also have this extra nice cardinality condition up here. All right, very important proposition that's used directly in the proof of Fermat's last theorem, which we will see much later. Proposition 3, let's let P be prime and let's let X be a finite GP module. Okay, so GP is acting on X here. Then it turns out the size of H1 GPX over the size of H0 GPX times the size of H2 GPX. So we got all the relevant group cohomology groups on the left-hand side for the action of GP on X equals the size of H1 GPX over the size of H0 GPX times the size of H0 GPX star. And these quotients are important because both of them equal P to the p-adic valuation of the order of X power, okay? And so the first equality essentially follows from local Tate duality, and the rest is covered in MAD chapter 1 as well, along with local Tate duality itself, okay? And so we'll begin shortly here over the next couple of videos, looking at how to do some relevant computations with Galois cohomology used in the proof of Fermat's last theorem. So I'll see you then, and thanks for watching.